The ideal gas law relates the pressure, volume, temperature, and molar amount of a gas with the formula PV equals nRT, where P is the pressure in kilopascals, V is the volume in liters, N is the molar amount of the gas, R is the universal gas constant, and T is the temperature in kelvins. An ideal gas law experiment uses 0.011 moles of a gas at a temperature of 273.15 kelvins. In part A, if the temperature and molar amount of the gas are held constant, the ideal gas law follows a reciprocal relationship and can be written as a rational function, P of V. Write this function. Rewrite the ideal gas law, PV equals nRT. Divide both sides by the volume to isolate pressure. Volume is the independent variable and pressure is the dependent variable, so pressure is a function of volume. We can write this as P of V equals nRT times 1 over V. We are highlighting the reciprocal nature of this function by separating the constants from the variable. Now we'll move on to part B. If the original volume of the gas is doubled, how will the pressure change? Rewrite the pressure function. Double the volume and plug this in on the right side of the function. Factor out 1/2. When the volume of the gas is doubled, the pressure will be 1/2 the original pressure. When the volume of the container is doubled, the gas molecules will hit the sides of the container less often, decreasing the pressure. Now we'll move on to part C. If the original volume of the gas is halved, how will the pressure change? Rewrite the pressure function. Halve the volume and plug this in on the right side of the function. The reciprocal of 1/2 is 2. When the volume of the gas is halved, the pressure will be double the original pressure. When the volume of the container is halved, the gas molecules will hit the sides of the container more often, increasing the pressure. Now we'll move on to part D. If P at 5.0 liters equals 5.0 kilopascals, determine the experimental value of the universal gas constant R. Let's take a moment to analyze the statement P at 5.0 liters equals 5.0 kilopascals. When the volume is 5.0 liters, the pressure is 5.0 kilopascals. We also know from the question that there are 0.011 moles of gas and the temperature is 273.15 kelvins. Collect all the known data for this question. Rewrite the pressure function. Plug in the known values. Multiply both sides by the volume to eliminate the fraction. Divide to isolate R. The value of R is 8.3 kilopascals times liters over moles times kelvins. In part E, complete the table of values and draw the graph for this experiment. Begin by writing a simplified function that we can use to quickly calculate the pressure. Rewrite the pressure function. We know the values of N, R, and T. They are held constant throughout the experiment, so plug them in. Multiply the constants to get 25 kilopascals times liters. When the volume is 0.5 liters, the pressure is 50 kilopascals. When the volume is 1.0 liters, the pressure is 25 kilopascals. Complete the rest of the table. Use the table of values to draw the graph. Now we'll move on to part F. Do the results from the table match the predictions in parts B and C? Bring up the completed table. In part B, we found that doubling the volume halves the pressure. In the table, we can see that when we double the volume, the pressure is halved. In part C, we found that halving the volume doubles the pressure. In the table, we can see that when we halve the volume, the pressure is doubled. The information in the table, and therefore the graph, matches our predictions in parts B and C.